All right, this is section 1.4, continuity and one-sided limits. So let's start with the definition of continuity. A function f is continuous at c when three conditions are met. F of c is defined, so the function is defined at that point. The limit as x approaches c of f of x exists, and the limit as x approaches c of f of x equals f of c. So we could use direct substitution there. A function is continuous on an open interval a to b when the function is continuous at each point in the interval. A function that is continuous on the entire real number line, negative to positive infinity, is called everywhere continuous. There are three specific conditions that ruin continuity. Number one, the function is not defined at x equals c. That is this first picture here. There's a hole in my graph, it's not defined there. The limit of f of x does not exist at x equals c. That's the second picture here. If there's like a jump or something like that, that's the second condition that ruins continuity. And number three, the limit of f of x exists at x equals c, but it is not equal to f of c. That's this third condition right here. That's when we have a hole in our graph and a removable discontinuity. So for discontinuity, if a function f is defined on an open interval I, except possibly at c, and f is not continuous at c, then f is discontinuous, and we say f has a discontinuity at c. There are two types of discontinuity, removable and non-removable. A removable discontinuity means that f can be made continuous by appropriately defining or redefining f of c. A non-removable discontinuity means f cannot be made continuous. Removable is generally your hole. A little hole in the graph, that's a removable discontinuity. Non-removable discontinuity, that'll be like a gap or a jump, something like that. So if we look at those same three pictures we just saw, the first one is a removable discontinuity. I just need to define that one point. The second one here is non-removable because there's a big jump. I can't simply fix it. And the third one is removable because I could just redefine this one point into that hole. So let's talk about the continuity of each function. First thing you have to think about, though, is the domain. The domain of the function 1 over x is everything except 0. And there are no gaps or holes or anything on the actual graph besides at x equals 0. So we say it is continuous on its entire domain. But there is a discontinuity. So it's discontinuous where that gap or hole or asymptote is. That asymptote is at x equals 0. So we would also say non-removable discontinuity at x equals 0. Because it's an asymptote and the graph kind of goes like that when we approach our asymptote. So that's non-removable. Letter B here, x squared minus 1 over x minus 1. I know that this has a issue at x equals 1. So that means it's definitely discontinuous somewhere. But on its entire domain, it is continuous, and I could verify that by looking at the graph. So everywhere except 1, it is continuous. So continuous on entire domain. But then I'll look at, can I rewrite this? If I factor the numerator, get x plus 1 times x minus 1 over x minus 1, and then that becomes x plus 1. Well, that's just the line. So if I can rewrite it so that there's no gap, hole, no issue in the domain, that's a removable discontinuity. So we'd say a removable discontinuity at x equals positive 1, because that's what made the denominator 0. So non-removable, I can't just redefine or rewrite my function. Removable, if it's something like this, that cancels out, and I could just say, all right, well, at x equals 1, here's what the function should equal. should equal 2. All right, for C, we have a piecewise function. For a piecewise function, we need to look at coming in from the left and coming in from the right at 0. So 0 is our potential discontinuity. So the top function, when I evaluate at 0, I get 1. The bottom function, if I were to evaluate at 0, I also get 1, which means it's continuous everywhere. Even though I can't actually plug 0 into the bottom portion of this function, if the two sides match up, then it's continuous. And then we have y equals sine of x. If you remember sine of x, it looks like this, right? Ooh, my really good, super fast sketch. That is everywhere continuous also. No gaps, no holes, no asymptotes, no nothing. So now let's talk about one-sided limits and continuity on a closed interval. A one-sided limit is from only the left or the right, not both. So only values less than my C, we'll call it, or only values greater than C. The limit from the right, or the right-hand limit, x approaches C from values greater than C. We notate it as limit as x approaches C with a little plus. Notice that's like a little exponent type thing on this little already small portion. So limit as x approaches C from the right of f of x equals L. So that means I'm coming in from the right. The limit from the left-hand limit, x approaches C from values less than C. We write that as the limit as x approaches C with a little negative. F of x equals L. That's coming in from the left. So we're going to find the limit of the square root of 4 minus x squared as x approaches negative 2 from the right. So coming in from the right, I'm using values greater than negative 2. So if I make myself a table, I could use negative 1.5 or negative 1.9, negative 1.99. We can't get to negative 2. So let's grab my calculator. The square root of 4 minus negative 1.5 squared. 1.323. Then change that to negative 1.9. I get 0.624. Make it 1.99. I get 0.1997. Looks like it's getting smaller. And I can't really tell what it's doing yet, so I'm going to try more values. Let's try negative 1.999. I get 0. I'm just going to put them over here because why not? 0.063. How about negative 1.9999? .02. Looks to me like it's getting smaller and smaller and smaller. So I'm going to say that the limit as x approaches negative 2 from the right of the square root of 4 minus x squared equals 0. I can verify this by looking at the graph. The graph of this function is actually a semicircle. So it's the top half of a circle with a radius of 2. So as I approach negative 2 from the right, I am approaching a value of 0. Notice that I had to do the limit from the right because from the left, that function does not exist. Then there's a couple special functions. Step functions are piecewise constant functions. So basically, somehow the endpoints will be defined, and then you step up. They just look like this. Then we have the greatest integer function. The greatest integer function is denoted as this. You got like double brackets with an x inside. That's the greatest integer n such that n is less than or equal to x. The graph of the greatest integer function is actually the one I just drew, but each integer, it hops up. This always rounds down. Sort of put that in quotes because even if it's 1.7, it rounds down to 1. So let's find the limit of the greatest integer function as x approaches 0 from the left and from the right. So the limit as x approaches 0 from the left of the greatest integer function, and the limit as x approaches 0 from the right of the greatest integer function. So as I come in from the left, these are values less than 0. So if I think of negative 0.5, well, it always rounds down to negative 1. Negative 0.2 will round down to negative 1. So as I come in from the left, I'm always going to get negative 1. As I come in from the right, these are values greater than 0. So 0.5 rounds down to 0. 0.2 rounds down to 0. So the limit from the right is 0. Then we have the definition of the existence of a limit. Let f be a function, and let c and L be real numbers. The limit of f of x as x approaches c is L if and only if the limit from the left and the limit from the right are both equal to L. So the limit only exists if both of the limits from the left and right are the same value. And then the definition of continuity on a closed interval. A function f is continuous on a closed interval if it's continuous on the open interval, all right, which we were just dealing with, and the limit as x approaches a, so the first number from the right is f of a, the limit as x approaches b, the end value, is f of b. So the function is continuous from the right at a and continuous from the left at b. So let's determine the continuity of this function. For this function, we need to think about the domain. When I think about the domain, I know that 1 minus x squared has to be greater than or equal to 0. So negative x squared has to be greater than or equal to negative 1. Divide by negative 1. X squared has to be less than or equal to 1. Square root both sides, we get negative 1 is less than or equal to x is less than or equal to 1. So our domain is negative 1 to 1. I want to know if it's continuous on that domain. Well, there's no gaps, holes, or any issues like that, so we know it's continuous on the closed interval. The only way we know it's continuous on the it's continuous on the open interval. The only way we know it's continuous on the closed interval is if we check those endpoints. So I need the limit as x approaches negative 1 from the right, and the limit as x approaches positive 1 from the left. So if I plugged in negative 1, I get 0. All right? If I look at a graph or plug in a whole bunch of values, I also get 0. And since that equals f of negative 1, we're continuous there. Then I try positive 1 from the left. If I plug in positive 1, I get 0. If I start plugging in values less than positive 1 but approaching positive 1, I still approach 0. So that is equal to f of 1. So we know that this function is continuous on the closed interval negative 1 to 1. Some properties of continuity. If b is a real number and f and g are both continuous at x equals c, then these functions are also continuous at x equals c. The scalar multiple, so b times my function, is still continuous at x equals c. The sum or difference of two functions that are continuous are still continuous. The product of two continuous functions is continuous, and the quotient of two continuous functions is continuous, except when the denominator is 0. There are some special functions that are always continuous at every point in their domains. Remember, this means there's discontinuity at values not in the domain. So polynomial functions are always continuous at every value in their domain, which is all real numbers. Polynomial functions are always everywhere continuous. Rational functions are continuous on their domain. So that's when the denominator is not equal to 0. Radical functions, an nth root is always continuous on its domain. Remember, you have to be careful of the domain. If it's an even root, you need a positive value inside of the square root, or inside of the root. And trig functions are always continuous on their domains. Sine and cosine are everywhere continuous. Tangent, cotangent, secant, and cosecant all have asymptotes, but they are continuous everywhere except those asymptotes. So let's determine why each of these are continuous. X plus the sine of x. Well, if I call g of x, x, I know that's continuous because it's a polynomial. And if I call h of x, the sine of x, I know that's continuous because it's a trig function. And if I just take g of x plus h of x, I know that's continuous because of those properties we just talked about. For g of x, we know that we have a number times the tangent of x. If I call f of x tangent of x, well, I know that's continuous on its domain because it's a trig function. And 3 times a continuous function is continuous because of those rules we just talked about. And then h of x here, h of x equals x squared plus 1 over cosine of x. I call f of x the numerator, x squared plus 1. I know that's continuous because it's a polynomial. And if I call g of x cosine of x, that's continuous on its domain because it's a trig function. And now I have f of x over g of x is continuous because when you divide two continuous functions, it is continuous except when g of x equals 0, because g of x cannot equal 0 because that would make the denominator 0 and then the world explodes. All right, continuity of a composite function. If g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x, or f of g of x, is continuous at c. So let's test for continuity. F of x equals the tangent of x. Well, we know that is continuous on its domain. Since it's a trig function. But that means that it's not continuous at values not in its domain. And tangent has asymptotes every odd pi over 2. So I could say it's continuous on the interval from negative pi over 2 to positive pi over 2. And then positive pi over 2 to 3 pi over 2. And then 3 pi over 2 to 5 pi over 2. And on and on and on. Hopefully you see the pattern now. For b, we need to determine the continuity of this function. Well, the sine of 1 over x. Everywhere but 0, is that continuous? Well, yeah. We test for continuity with 3 things, right? We test for, does g of 0 exist? Well, it does. It's 0. Then we test the limit. The limit as x approaches 0. I know 0 is the potential issue because that's where it switches. G of x. Limit as x approaches 0 of g of x. Well, that's everywhere. That's the sine of 1 over x. And in a previous lesson, we talked about how the sine of 1 over x, that limit does not exist. So this continuity is not continuous because the limit fails to exist. We have discontinuity at x equals 0 because the limit as x approaches 0 of g of x does not exist. And then h of x. For h of x, we're actually going to use the squeeze theorem. So we start off by checking, does g of 0 exist? Yes, it does. It's 0. Now we need the limit as x approaches 0 of my function. Oops, h of x, not g of x. H of 0. So we can't evaluate this just straightforward like. But we do know that sine always gives us a value between -1 and +1. So the sine of 1 over x, no matter what's inside here, sine is between -1 and +1. So that means my function just has an x multiplied in there. So my function is between negative whatever x was as a negative value and positive whatever x is switched to positive. Well, I can take a limit then. The limit as x approaches 0 of negative absolute value of x is 0. And the limit as x approaches 0 of positive absolute value of x is 0. Okay, so that means that the limit of h of x has to be in between those two values. Since the function is always between those two functions, the limit has to be between those two limits. But both of those limits are 0. What's the only way for a value to be between 0 and 0? Well, it must be 0. So the limit equals 0. And that does also equal h of 0. So therefore it's continuous at 0, and we know it's continuous everywhere else also. So this function is everywhere continuous. That is the squeeze theorem at work for you. And now a very important theorem, the reason that it has stars by it, the intermediate value theorem. We'll be doing a lot with this one as we go forward too. But if f is continuous on the closed interval a to b, f of a is not equal to f of b, and k is any number between f of a and f of b, then there's at least one number c in the interval a to b such that f of c equals k. Basically, what this says is my function is continuous between a and b. So that means no holes, no gaps, whatever. F of a is not equal to f of b, right? Those two are not the same height. If I pick any value, k, in between f of a and f of b, okay, there's f of a, there's f of b, let's say I pick k right there. There has to be at least one value, which we'll call c, that has that k value as its output. This picture I drew has 3 of them. This is something called an existence theorem. It states that something exists, but it doesn't give us any methods to find it, so we'll have to do a lot of work with that. The intermediate value theorem can be used to find zeros of a function. If f is continuous on a to b, and f of a and f of b differ in sign, then there's at least one 0 in the interval. So I'll draw you 2 pictures of this. The first one, let's say f of a is positive, and f of b is negative. Here's a, here's b. Is there any way for me to draw a continuous function that doesn't cross the x-axis in between there? The answer is no. So, no matter what I do, there has to be at least one 0. For my second picture, I'll draw it the opposite way. F of a is negative. F of b is positive. They differ in sign. Is there any way for me to connect these without crossing the x-axis? Again, the answer is no. I need to have at least one x-intercept in there. So let's use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0 to 1. We're not going to find the 0, just show that it has one. So the first thing is f of x continuous? And yes, f of x is continuous because it's a polynomial. Then we have to show f of a and f of b. F of 0 is, plug that in, I get -1. F of 1 is 2. Those differ in sign. So now I can say since f of 0 is less than 0 and f of 1 is greater than 0, there must be at least one value, we'll call it k, on the interval 0 to 1, such that f of k equals 0. I don't know what it is, I don't care what it is right now, but I know it exists. So now you'll try some.